How to build a lightweight network SLA monitoring platform with Python and TimescaleDB. In many industrial environments, managing remote network nodes means relying on raw terminal diagnostics. When an issue occurs on a distant segment, the immediate reaction is to fire up a continuous ping loop, forcing you to stare endlessly at scrolling text to track state changes in real time. This method collapses entirely the moment you step away from the desk. During an operational review, you are left completely unable to answer the most critical questions. When exactly did the path degradation begin, and how long did the outage actually last? Relying on these manual observations creates a massive accountability deficit. Without a reliable, persistent historical record, it is mathematically impossible to empirically prove the real-time latency against a provider's guaranteed service level agreement. Standard tools often pull a single ping every 60 seconds. If a transient patch of network jitter drops that single packet, the tool falsely logs a hard outage, creating rapid, artificial state flipping that ruins the integrity of your data. Legacy enterprise relational platforms solve the data retention issue, but they demand constant administrative overhead. If your monitoring server requires a simple OS patch or a reboot, you have to manually toggle all your infrastructure into a maintenance state. Otherwise, the database aggressively logs the server's downtime as a massive outage across all remote endpoints. Public SaaS utilities offer a frictionless alternative, elegantly handling onboarding and historical gaps. Yet, because they pull exclusively from public cloud infrastructure, they are entirely useless for tracking internal nodes tucked safely behind an enterprise WAN boundary. The industry is missing a secure, self-hosted engine capable of recording objective mathematical truth without requiring manual database queries or constant administrative handholding. To solve the data ingestion problem, this platform utilizes a high-fidelity subcycle. Instead of a single check, it fires 10 pings inside each minute window, spacing the packets exactly 6 seconds apart. Storing high-frequency per-packet logs triggers rapid disk bloat. To prevent this, the engine calculates the metrics entirely in memory, writing only a single summarized row to the database every 60 seconds. This table shows how we track the raw per-minute truth. Based on the 10-packet success rate, we assign one of 4 detailed states. These range from a perfect up to up unstable, down unstable, or a completely dead down. We then map that detailed volatile state into a normalized operational state. If a link drops 2 out of 10 pings, it is technically unstable. But it still passes production traffic. Therefore, its macro operational state remains safely marked as UP. Intentionally decoupling raw packet loss from the final operational state eliminates alert fatigue and keeps your long-term historical logs remarkably clean. Clean logs are only useful if the resulting math is accurate. We implement a concept called lifespan alignment to fix mid-month onboarding distortions. This ensures that missing data points from before a device existed don't penalize its final score. This timeline graph demonstrates our boundary logic. The system strictly enforces that a reporting window cannot begin before the device's exact creation timestamp in the database. The next challenge is the unknown state, caused by internal server blackouts. We track those known offline seconds and dynamically subtract them from the total elapsed lifespan denominator. If a remote switch was registered 30 days ago, and the internal monitoring server goes offline for a 2-hour software upgrade, the platform sets your true SLA denominator to 30 days minus 2 hours. The missing data is completely neutralized, and the remote hardware avoids an unfair performance penalty. By integrating these mathematical timeframe corrections directly into the application layer, the platform guarantees objective truth straight out of the box, sparing the engineer from writing complex database queries. To achieve this with the lowest possible overhead, we assembled a minimalist stack. We used native Python asynchroneo for single-threaded concurrency, the FastAPI framework for backend routing, and Vue.js for a lightweight presentation layer. For the database, we selected TimescaleDB. Instead of buckling under persistent logging, it automatically partitions metrics into time series chunks, keeping query speeds instantaneous even across a multi-year retention window. Transitioning from network engineering to full-stack development meant facing a daunting wall of boilerplate code. We used modern AI coding companions to rapidly scaffold the initial framework, spin up routers, and iterate on table schemas. But the AI faltered against low-level infrastructure constraints. It routinely failed to handle the syntax for unprivileged Linux network sockets, regular expression parsing for system ping fallbacks, and microsecond-level timing loops. AI can instantly generate structural frameworks, but engineering a reliable hardware-level state machine still demands rigorous manual intervention and testing inside a laboratory environment. We deliberately reduced the project scope, cutting out features like automated trace routes and quality of service analysis. By narrowing the focus purely to ICMP availability and accurate historical analytics, we maximized the core architectural reliability of the platform. The full architectural breakdown and the complete open-source codebase are available on my website at kennethnorum.com. The link is in the description below. Engineering your way through daily operational constraints is the ultimate method for transforming chaotic network visibility into a reliable, automated ledger.